Hi! Hey guys, we made it! We made it to the fundamental theorem of calculus. This is a theorem that's going to relate derivatives and integrals over a specific domain of the independent variable. Alright, the FTC is stated as follows. If we have a function capital F of x whose derivative f prime is equal to little f of x, then when we integrate little f of x over a specific domain from x equals a to x equals b, that is equivalent to evaluating the antiderivative capital F of x at b and then subtracting the evaluation at a. What? Okay, so let me write this down in words. Hopefully we can understand this a little better. Let's start with the right-hand side over here. So our original total function was capital F of x. What does f of b minus f of a represent, where a and b are two values for x? Well, that's the difference between evaluating it at b and evaluating it at a. So in words, the expression on the right here is the total change in our capital f of x, our total function, from the point where x equals a to the point where x equals b. Alright, so that total change can also be represented over here in integral format as the sum of a bunch of instantaneous rates of change from x equals a to x equals b. Alright, this fundamental theorem actually gives us a way to calculate what we call definite integrals. Up to this point, we have only been working with integrals which do not have letters on the bounds or numbers on the bounds. Those are called indefinite integrals. A definite integral is one where you're going to see a little number or letter on the bottom here and then another one on the top here, and that tells you that you're only interested in analyzing that integral over a specific domain of the independent variable. Okay? Actually, there's another way to say that in pictures. The definite integral of little f of x dx from x equals a to x equals b is represented by the area under little f of x from x equals a to x equals b. Okay, so let's take a look at a picture. Here we have a picture of the derivative function little f of x, which remember is the derivative of some total quantity capital F of x. Okay, so right here I'm plotting the rate of change, the value of the rate of change. Now what I'm saying is that when I specify some bounds on my integral from x equals a to x equals b, what I'm actually doing visually is I'm describing an amount of area underneath the curve of f of x from x equals a to x equals b. Okay, so when the integral doesn't have these little numbers on the top and bottom, you're used to getting a function as the answer for the output, right? Usually it's some capital F of x plus c. But now when we put in the bounds to define the domain over which we're interested in, now you're going to see that the answer to a definite integral is actually a numerical value. And that value represents how much area, I've shaded right here, is between f of x and the x-axis. Alright, that actually makes it really useful for calculating some areas that might seem hard to calculate. Like, for example, the shape that I just shaded right here, what kind of shape is this? Is it a square? No. Is it a circle? No. Is it a triangle? No. It's not something where I have a formula that I could actually calculate the area for. And that happens a lot in real life. We might need to know the area of something, and that thing is not a perfect shape that we have a nice formula for. So how are we supposed to find the area? We're actually going to use calculus and the concepts of integrals to find the area for us. Alright, so here's the strategy, and actually this is what is actually represented by the integral sign. This integral sign right here, in case you've ever wondered where it comes from, is it's actually an elongated S. It's the letter S that's been stretched out, and S stands for sum. So the integral sign actually means sum. And what is it the sum of? It's the sum of a bunch of areas of little rectangles. Okay, so if somebody told me to add up the area underneath here, add up the area of this shape right here, it would be kind of hard for me to do. Like we were saying, it's not a shape whose area I know. But I know how to calculate the area of a rectangle, right? Of the shape of a rectangle. I know that the area of a rectangle is always its width times its height. So my strategy here is that I'm going to take the area in question and I'm actually going to break it up into a bunch of little rectangles whose heights I know they are described by the function value of f of x and whose widths I'm going to specify. Alright? Now you can see that if I use a couple big rectangles, I'll get a sort of okay approximation. If I use these skinnier rectangles, I'll get a better approximation. And if I even use skinnier rectangles still, I would get an even better approximation of the exact area under this curve. Okay? What happens in the integral format here is that I've defined a specific width that I want to use. Let's say the width of my rectangle right here, I'm going to call it some teensy amount. I'm going to call it dx. Okay, so let's say the width of this rectangle is dx. Well, what's the height of this rectangle? Well, I mean, it's about as high as the function goes up because I'm trying to calculate the area under the curve. So it looks like the height of this rectangle is f of x for whatever value of x I'm at inside the interval. And the width of the rectangle right here, the width is actually dx. And I know that the area is always width times height of a rectangle. Okay? And that's why the integral says integral, which we now know means sum. So add up all of these quantities, the height times the width of a rectangle, which represents the area under the curve. Okay? So I'm going to do this again and again for each little rectangle that I draw between the point x equals a and x equals b. To make it simple on myself, I'm going to define a specific little width dx. I'm going to consistently use the same dx for the width. And then each one of the heights, I'm just going to approximate as f of x, where the x that I use for the approximation is going to be some value inside that interval of the dx. So actually, I'm not really going to write down any more than this. You can see your textbook if you want to see the definition of what's a Riemann sum. I'm trying to describe Riemann sums to you right now. When we take the integral, we actually, in the integration technique, we actually let the dx tend towards 0. Okay, now this takes us all the way back to the beginning of the course where we talked about limits. Remember when we were defining the instantaneous rate of change, we had 2 points on a curve, and then we limited the distance between them until they came closer and closer together, became the same point? There's a similar definition of the definite integral in terms of the limits of a bunch of areas of different rectangles known as a Riemann sum. Okay, so inside this definition, you can see that although I'm trying to make an approximation of the area under this curve, I would get exactly, precisely, the exact area under the curve if I let each of these rectangles have tiny, tiny little width, which is to say that I let the width dx go to 0. Okay? In the limit, as dx goes to 0, the sum of all the heights times the width of all these rectangles added up is going to give me exactly the area under the curve from x equals a to x equals b. Alright, so now we understand the definite integral a little better as representing the area under the curve, but over here, the FTC says that the area under the curve of all the instantaneous rate of changes is equal to the difference of the antiderivative evaluated at the two endpoints. So now let's see how that concept relates to this area under the curve concept. Okay, so I'd like to use a classic example where my total function, capital F of x here, let's let capital F of x be the distance that I've traveled. Let's pretend I'm in my car driving on the road somewhere, and capital F of x is the total distance traveled in miles. Okay? And then if I take the derivative of that, if I take f prime of x, which is little f of x, that would be the instantaneous rate of change of the amount of distance that I've traveled. The instantaneous rate of change of my position is going to be my velocity. Okay, so this is going to be my velocity, and you can see that if if x here is in hours, and capital F is in miles, then the little f of x is going to be in miles per hour. Okay, so you can kind of think of this as the speed of a car, and you can think of this one as the distance traveled or the position of the car on the road. Alright, now let's graph the little f of x here, and then we'll turn it over to the big capital F of x here. Alright, let's start out with the simplest example possible. Let's pretend I'm just going to go a constant speed, and let's say that speed is 60 miles per hour. Okay? Now, if I wanted to calculate the definite integral from, let's say, 0 to 1 of little f of x dx, not only does that represent the area underneath this curve, little f of x, from the point x equals 0 over here to the point x equals 1, but that also will be equal, according to the FTC, to the difference between f of 1 minus f of 0. Alright, now let's try to calculate this, thinking about it geometrically. I've picked this simple shape where the height's not changing at all. So this definite integral is representing the area under this curve. Okay, now that's a normal shape that I know the equation for the area of. The width of it is 1 and the height of it is 60, and so the total area here is 60 times 1, which is equal to 60, right? 60 is the number that I get out of this definite integral, and so 60 must be the number that I get when I calculate the difference between capital F of 1 and capital F of 0. Okay, now let's just, for the sake of argument, pretend that we started at position 0, so that F of 0 is equal to 0. So that means that when I get over here to 1, F of 1 right here has got to equal 60. Alright, because then I'm going to get 60 minus 0 is equal to the 60 that represents the area under this curve. Sure enough, that is going to be equal, and also, if we replace this f of x with the number 60 miles per hour, which it is right there, if I asked you for the indefinite integral, the integral of 60 dx, what would the answer be? The integral of 60 dx, that's 60x, right? Because if I take the derivative of 60x, I get 60. And so really over here, I'm going to be graphing the function 60x. Capital F of x here is the function 60 times x. Oh, nice! And so here, this is representing how far I've gone when I'm traveling at a constant rate. Okay? And you can see that f of 1 on the curve 60x is 60, and f of 0 is 0, and I'm just traveling linearly just like that. Alright? Now, let's say I wanted to change my integral, so I was just going from 0 to 1/2. That would just be the area from x equals 0 to x equals 1/2. And how far will I have gone if I travel 60 miles per hour just for 1/2 of an hour? That would only be 30 miles, right? And so what that would be is f of 1/2 minus f of 0. And you can see that right here, f of 1/2, sure enough, f of 1/2 is 60 times 1/2, and that would equal 30. Okay? So what we're trying to say here is a relationship between a total quantity and its corresponding instantaneous rate of change is that if you add up all those little instantaneous rates of changes over a specified interval, that's the same thing as calculating the difference between the two endpoints of that interval on the corresponding antiderivative. Now in the next set of videos, I'll show you lots of examples so you can get the hang of this.